Welcome to the first lecture video recording in our Class 22 series of lecture videos. Here we have, at the very top, we have a hydrogenation of this trans 2-butene that's substituted with deuterium at the alkene carbons. And so we ended our last video for our Class 21 series of videos saying that for hydrogenation we have syn addition, so those hydrogen atoms are added to the same side, or the same side of the two different faces of our alkene, and so we could get both of those hydrogens being put on the back side of our alkene, which would give us this hydrogenated product. And so we have an R and an R stereocenter there. Or we could get our hydrogen atoms placed on the front face of that alkene, which would give us the S and the S stereocenters. This is a racemic mixture of enantiomers. There's no energy difference in the transition states, whether those two hydrogens go on the back face of the alkene or the front face of the alkene. This particular alkene, however, we already have one stereocenter. It is chiral, and now there is an energy difference as to where those two hydrogens go, because we have diastereomers being formed. We can either put those two hydrogens on the back face or the front face, and indeed it's easier for this alkene to adsorb onto our palladium surface from its back face, because we have this tert-butyl group coming up and shielding that top face of the alkene, so the hydrogens go on the back face. This is hopefully understandable. If it isn't, please bring it up during the class time, or come visit me in office hours, or pester your SI about this. Something that's pretty important to keep in mind concerns the thermodynamics of alkenes. Here we have we have 1-butene. We're going to hydrogenate it to butane. We get 30.3 kcals per mole out. Here we have cis-2-butene, and we hydrogenate it, and we only get 28.6 kcals per mole out. What about trans-2-butene? Even less energy comes out when we hydrogenate that. We get 27.6 kcals per mole out. And so what I am trying to illustrate here is that the more alkyl substitution you have on your alkene, the more stable it is, the lower in energy that is. So here we've got a dialkyl substituted alkene, and it's more stable than when we have just a monoalkyl substituted alkene. Of course, the trans substitution pattern is energetically more stable than the cis substitution pattern. There is steric repulsion between these two hydrogens, so it's slightly higher in energy than this trans substituted, alkyl substituted alkene. But what's important for you to note beyond that relationship is the more alkyl groups you have on your alkene, the more stable it is. This will factor into reaction mechanisms that we will see as to whether the reaction is kinetically or thermodynamically controlled. What is the favored product that we might expect? Usually when something's thermodynamically controlled, you expect the most stable in energy, the lowest in energy type of product. So more alkyl substituted alkenes are more stable, lower in energy. Trans alkenes are more stable than cis alkenes in general, and that's because of sterics. That's what's illustrated with these little repulsive annotations. This is not necessarily true when the double bond is in a ring. You could try, for example, building a molecular model of cyclohexene. Yes, you can only accommodate that double bond with a cis substitution pattern. I've drawn a trans substitution for that double bond in the 6-membered ring, but if you tried to make this with your model, you would break plastic bonds. It's just not feasible to have a trans double bond in a 6-membered ring. An 8-membered ring, in fact, is the first ring size that can accommodate a trans double bond. Here we have a tetraalkyl substituted alkene. That's going to be more stable, so lower in energy than this trialkyl substituted alkene, which is going to be more stable than this trans dialkyl substituted alkene. So tetraalkyl substituted alkene is more stable than trialkyl substituted, etc. So how does this come into play? Again, like I said, it can come into play when you're thinking about what kind of products you might produce from a given reaction. Here we have sodium methoxide, we have this tertiary carbon electrophile good leaving group in DMSO. While we might be tempted to do an SN2, we know we can't do an SN2 on a tertiary carbon, it's just too sterically hindered. So now we have a choice. Do we pluck a hydrogen off of the beta carbon to give, this trialkyl substituted alkene, or do we pluck a proton off of this primary carbon to give this dialkyl substituted alkene? Well, this particular reaction is said to be under thermodynamic control. Our relatively strong base, our methoxide, is a small base. It's not necessarily big and bulky or sterically imposing, and so it can pluck a hydrogen off of our secondary beta carbon and give us this trialkyl substituted product, which is the most stable product, as our major product. Hence, the reaction is under thermodynamic control. When we change that strong base to something like potassium tert butoxide, now instead of that methyl group, we've got this tert butyl group on the other side of our oxygen. And so that's fairly big and sterically imposing. It might be difficult for that base to access that secondary beta carbon to pluck a proton off of it. It might be much easier to access one of these primary methyl carbon hydrogens. And so, yes, our major product is the less stable alkene. It's the dialkyl substituted alkene versus a minor product where we have the more stable trialkyl substituted alkene. So we say that this reaction is under kinetic control. The lowest energy activation energy pathway for that tert butoxide will be to pull a proton off of one of those primary methyl beta carbons. So that pretty much does it for this first lecture video. Good luck with the question, and I'll see you in the next.